So it's lecture 6. So this course has a lot of different topics, and just to put this in context, let me just do a quick recap of what we've done so far. Wait a second, what's going on with my stuff? Just a second. So yeah, it's okay. That's kind of weird. It was working a moment ago. Keep it like this. Okay, just a second. Okay, let me just see if it works with the other whiteboard. Okay, well, at least I can write here. I'm not really sure what's going on with my computer. Let's try this one more time. I'm just going to use the other whiteboard. I'm guessing it's just time for me to get a new computer. Okay. So it's lecture 6. And just a recap of what we've done so far in the course over the last few weeks. So in lectures 1 and 2, we talked about propositional logic, and at a high level, we discussed how to read, write, and interpret mathematical statements with a precise meaning. Yeah, the precise meaning and truth value.
I have a quick question about the first and the second lecture. So how can we distinguish whether like it is like a propositional function or like it's just a sentence describing
a propositional function has a variable in it. That's the difference, right? So a propositional function is something which has a variable, becomes a proposition when you substitute the variable.
But the outcome is just like true or false.
Yeah, it's always it's still a proposition. Lecture 3 was about how to construct, read, and write proofs to establish these truth values. And that'll be an ongoing thing in the whole course, not just lecture 3. And then lectures 4 and 5 are about sets and functions, which are basic structures that we'll use to describe many mathematical objects. And we also discussed this notion of cardinality, which is a way to measure sizes of infinite sets. Finite or infinite sets. And I want to make a few remarks about what we've done so far. So one is that definitions are really crucial. If you don't know the definitions, you don't even know what statements mean. So you must know the definitions exactly. There's no really leeway there. So you must know the statement, and if you know what the statement means in a precise way, that will guide you as to how to prove something satisfies that definition, how to check that something satisfies that definition, how to use the assumption that something satisfies that definition. The second thing is when you use a variable, you must be aware of its quantification. So is it arbitrary? Is it some specially chosen variable? And also its type. So by type, I mean, is it, is it a set? Is it a function? Is it an element of a set? Is it a number? All these things are different. And this is like a basic grammar check that, you'll easily catch yourself writing something nonsensical if you see that it doesn't have the right type. And another general comment is I've been talking about the table during the last few lectures, and somebody pointed out on Piazza that I never precisely defined it. So really what this is a metaphorical space in your head where all of this information is stored for bound variables and statements either known or assumed to be true. While you're reading or writing a proof. So that's, it's kind of like your working memory. A proof is in some ways like a computer program. You run it on your mind, and the table is sort of the working memory of what's going on in the proof. And one specific clarification involving lectures 3 and 4 so in lecture 5, we actually looked at two different concepts. If you have a function from a set A to a set B, and you have a subset S of B, then you have F inverse S, which is the inverse image of B. So it's a set of F of A. Oh, sorry, I have it backwards. So it's a set of A in A such that F of A is an S. This is the inverse image. But you have this other notation, F inverse B, right? So this is just the inverse function, F inverse, applied to some element of B. And these are different concepts. So this is inverse image of a set S. And the last one is the inverse function. And in particular, okay, so the way you tell the difference between these is that this is a set, this is an element, right? So this is a subset of B, S, whereas B is just little b is an element of B. So these are different concepts, right? This is an inverse image, this is inverse function. And this only works for F of bijection. In other words, an invertible function. Not all functions are invertible. So that's a confusing thing, but it's an important distinction to keep in mind. Okay, so that's all I want to say about the previous material. Now, the next few lectures, 6 to 9, we're going to do number theory, which is one of the oldest and still most mysterious branches of mathematics, which is about the study of the integers. And today we're going to cover 3 topics. So one is we're going to cover division and divisibility. So what does it mean to divide one number by another? Then we're going to cover a very important new, subject called modular arithmetic. And then finally, we're going to talk about representations of numbers. That's the outline for today. So let me start with item 1. So the key definition here is what does it mean for one number to be divisible by another. So if a not equal to 0 and b are integers, then we say that a divides b, and this is denoted a bar b like this, if there exists some integer k. So let's say it's an integer such that b is k times a. So this is not mysterious. This is a concept you've seen before in some form. And another way to view it is that this is just saying that when you divide b by a, this is an integer. It's not a fraction. So for example, 3 divides 9. So k in this case is just 3. 3 does not divide 10 because there's no number k, so that 10 is equal to 3 times k. So this is where it does not divide. Here's an interesting one. Does 3 divide 0? Any thoughts on that?
I think it does, because then like k is 0.
Yeah, it does, because 3 is, because 3 is equal to 0 times 0. So that's okay. Okay. Now, what are the basic properties of this notion? So there are 2 basic properties that we're going to use pretty heavily in this course and in this lecture. So the first is if a divides b and a divides c, then a divides b plus c and a divides b times c. So by the way, I made all this fuss about quantifiers, but I haven't explicitly written for all here. So this might seem a little sketchy to you, but what's the implicit quantifier here?
I mean,
all ABC.
Yeah, all ABC. So this is something that comes up a lot in mathematical writing, that sometimes in a statement of a proposition, you omit a quantifier when it's clear. If you just write if or suppose, that's assumed to mean for arbitrary integers. So integers is implicit because I use this bar notation, right, which only makes sense for integers. So this is the first one. And then the second one is if a divides b and b divides c, then a divides c. So any questions about the statement? I'll say a little bit about the proof in a moment, or the proof of one of them. Okay, so let's prove just one of them. I mean, they're all pretty easy. Let's just prove this one star for now. You get the idea. So it's a for all statement, right? So to prove it, I have to take some arbitrary integers. So suppose a B, C are integers, and A divides B and A divides C. I guess we shouldn't say and twice. Okay, now we want to show that A divides B plus C. Well, let's invoke the definition of divisibility, right? So because what does it mean A divides B? It means that there's some K, so that B is equal to KA. And similarly for A divides C. So let's choose integers K1 and K2 such that, so this is a shorthand. Well, okay, I'll just write such that. I'll use this in lecture, but I encourage you in actual writing to write it as full. Such that B equals K1A and C equals K2A. So now these K1, K2 are on the table. And so now what's the natural thing to do?
Add your equations.
Yeah, is that the equations? So notice that B plus C equals K1A plus K2A equals K1 plus K2A. So A divides B plus C. That's the proof. It's not complicated. And the other ones are similar. You just apply the definition. Okay, so those seem like some pretty basic properties. Any questions about that before we proceed?
Would we not have to define like K3 equals K1 plus K2?
No, it's implicit in the writing, right? So it's in the last line. I have grouped together K1 plus K2. And yeah, if I wanted to be really pedantic, I could say, you know, A divides B plus C because K1 plus K2 is an integer. But it's sufficiently clear. Like I have highlighted it by putting it in parentheses, and I'm just implicitly saying that.
Thank you.
Like the so A divides B plus C means thus the definition of A divides B plus C is satisfied. And it's kind of clearly demonstrated what is satisfying. Okay, so that's exact divisibility. Now let's talk about division with remainder. So this is something which is quite simple, but very important. So I'm going to call it a theorem. This is sometimes called a division algorithm. And a theorem is just an important proposition. It's not anything different. It's an important proposition is called a theorem. So here's what it says. If A is an integer and D is a positive integer, then there exist unique integers Q and R satisfying two properties. A is equal to DQ plus R, and R is non-negative and strictly smaller than D. That's called the division algorithm. This is just a formalization of what it means to divide an integer by another integer with remainder. It's not really a new concept, right? So it's something you've been doing since, I don't know what grade, I don't remember what grade I learned this in. This is a formalization of, the usual long division, right? Like let's say you do some division like this. Okay, I haven't done this in a while, actually. So if you do this, then this is the remainder, this is the quotient, this is the divisor, and this is your number A. So it's not really a new concept, but we just want to be, so we'll be dealing with negative numbers sometimes, and we want to, know which, we want to just nail it down. Okay, so this is the division algorithm. And I will not prove this. Let me tell you so there are two parts to this theorem, right? There's existence of these numbers Q and R. So these numbers Q and R, this is called so Q is called the quotient. As you know, R is called the remainder. And this is saying that there exists Q and R and they're unique. The uniqueness is important. It's saying that you can't do this in two different ways. There's only one choice of Q and R that have both these properties. And well, the idea behind the proof is not complicated. It's actually simpler than long division. In fact, long division is a pretty complicated algorithm. The idea is, well, just consider the integer number line. So let's draw a line. It has 0, and then it has some integers at evenly spaced. And then, so we're given A and D, right? So now just circle all multiples of D, the divisor D. So 0 is a multiple. Let's say, I don't know, let's say the divisor is 3, right? So 0, 3, 1, 2, 3. We'll circle every third, 1, 2, 3, etc., right? And the distance between any two of these is going to be exactly D. So now, okay, how do you find this quotient and remainder? Well, so you're given this Q, right? So let's suppose Q is over here. Let's star this. Let's suppose this is Q. Okay. So yeah, so given Q, choose Q times D to be the largest. So that means largest means rightmost on this number line. Multiple of D, which is less than or equal to A. Less than, sorry, Q is not given, A is given. What am I saying? A is given, right? The thing you're given is A, not Q. You're not given the answer when you do the division. Choose it to be the rightmost multiple of D such that QD is less than or equal to A. So that just means this closest circle, I mean, not closest, it means the largest one that's to the left of A. So in that case, that will be this one, right? So now observe that A is equal to QD plus R, for R just equal to A minus QD, which is non-negative because QD was less than or equal to A. So this is my QD. And R is just this difference. And clearly R is strictly less than D. Why is R strictly less than D?
Well, if if R was greater than D, then that would contradict our choice of Q.
Yeah, so formally you can say if R was bigger than D, then you could actually choose another multiple of D that's even closer to A. But from this picture, it's just clear that, you know, R is smaller than the gap between two of these circles. So R is less than D. This is not a formal proof. What you've said just now can be turned into a formal proof. Okay. So notice R less than D because the gap between circles is D. Okay, I mean, we'll do a formal proof of this later. This proves the existence. Okay, it's just a number line. It's not something complicated. Let me formally do the uniqueness proof. But any questions about this sort of sketch of the existence proof? Okay. Let's formally do the uniqueness proof. So uniqueness proof is saying there's only one Q and R with this property. Okay, so to prove uniqueness, let's assume two different Q and R and show that they have to be the same. So suppose A is equal to Q1D plus R1 and also equal to Q2D plus R2 for some integers Q1, Q2 in Z and R1 and R2 both non-negative and strictly less than D. I'm going to show that they have to be the same. So now I'm going to do something. I'm going to use a device which I discussed last time. I'm going to assume without loss of generality that R1 is greater than or equal to R2. So WLOG means without loss of generality that R1 is greater than or equal to R2. All that means is, well, one of them is bigger, and I can just name them so that R1 is the bigger one. Okay. So now I want to show R1 is equal to R2. Any thoughts on what I could do with the information I have on the table right now?
Think your screen's paused.
Already? Okay.
No, I don't think so.
Well, okay, let me just refresh it just in case. Can you see my screen now?
Yeah.
Yes, it wasn't paused.
Okay. Okay, good. Well, okay, I'm just going to subtract them, right? So observe that if you take the difference, R1 minus R2, that's equal to A minus Q1D minus A minus Q2D, which is just equal to Q2D minus Q1D, which is equal to Q2 minus Q1 times D. So what does this mean in terms of divisibility? Can people still hear
Oh,
me?
it means R1 minus R2 is divisible by D,
Yeah.
which suggests that the difference between R1 and R2 has to be like greater than or equal to D, which contradicts our choice of R1 and R2.
Yeah, or another way to put it, thus D divides R1 minus R2, but R1 minus R2 is strictly less than D, right? Because I chose R1 to be bigger than R2. So I have two numbers strictly less than D and I subtract the smaller one. So now D divides a number smaller than it. That's only possible if that number is 0. Okay, so that's the proof of the uniqueness. It's maybe a good example of a simple uniqueness proof. Any questions about that? Okay, so the notation we're going to use to talk about remainders. So remainders are going to be very important. Are A div D equals the quotient and A mod D equals the remainder. Okay, mod is short form for modulo. And this brings us to the next topic, which is modular arithmetic. So all you need to know is this division algorithm. Okay. So this is something you actually do every day, right? For example, let's say you sleep at 11 p.m. for 8 hours. You wake up at 19 p.m. No, right? You wake up at the remainder of 19 modulo 12, which is 7 a.m. Right? So we're actually doing this remainder thing all the time. We measure time as a remainder modulo 12. And okay, I mean, we also, in fact, anything periodic, I mean, even with time, right? So let's number the days of the week 0 through 7. So let's do Sunday, Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, 0, 1, 2, 3, 4, 5, 6. So today is Tuesday. That's number 2. You know, what day is it in a, you know, what day is it going to be in, I don't know, 39 days? Well, again, the day is just the remainder when you divide by 7. So it's going to be 2 plus 39, which is 41. 41 mod 7 is 6, right? Because 41 is equal to 7 times 5 plus 6. So the 6 is the remainder. And so it's going to be Saturday.
Can we do like 2 plus 39 mod 7?
Yeah, I'll get to that in a moment. So you're asking a great question. Could you do 39 mod 7 and then add that to 2? The answer is yes. I'm going to explain why in a moment. And now let's look at example 3. So let's say, so what day is it? What day is it in, I don't know, 2 to the 45 days? Okay, that's not a reasonable question. It's a type of thing that might appear in a sci-fi novel or something. By the way, how many people have read the 3-body problem? I highly recommend that you read this amazing sci-fi trilogy that came out a couple of years ago. But anyway, what day is it in this many days? Well, this is a bit tricky, right? This is some giant number, and we don't know how to write it down. So this brings me to modular arithmetic, which is a systematic way of talking about remainders and doing computations with remainders. So here's a key definition. For integers a and b, a is congruent to b modulo, or also m is an integer, or I guess m has to be positive. Okay, so let's just clearly specify this. For a, b integers and m a positive integer, a is congruent to b modulo m, denoted a, this triple equal sign b mod m, if a and b have the same remainder modulo m. Okay, so it's a new notion of equality, but it's not very complicated. It's just saying they have the same remainder mod m. Now what we're going to do is we're going to discover how these remainders change when you add and multiply numbers. That's what modular arithmetic is all about. And any questions about the definition before I do that? Okay, let me write down a useful proposition, which is simple to prove, which will be used in establishing the properties. This is that A is congruent to B modulo M if and only if M divides A minus B. So let's do the proof. So there are two directions, right? It's a biconditional. The first statement implies the second statement, and the second statement implies the first statement. Let's do the, so this direction is kind of easy, and I'll just leave this as an exercise. Let's do the other direction. So suppose M divides A minus B. Okay. Now I want to show that A is congruent to B modulo M. So I want to show they have the same remainder modulo M. So let's just write out by the division algorithm how A is related to its remainder modulo M. So let A equal to M Q1 plus R1 and B equal to M Q2 plus R2 by the division algorithm. So I'm implicitly saying, I can choose Q1 R1 and Q2 R2 so that A is equal to M Q1 R1 plus R1 and B is equal to M Q2 plus R2. I'm just saying divide A by M and divide B by M and see what the remainder is. And what's our goal? Our goal is to show that R1 equals R2. It never hurts to write down what you're going to show, just to remind both yourself and the reader what you're going to do in the proof. So, I mean, the key observation is let's just divide them. Observe that A minus B is equal to M times Q1 minus Q2 plus R1 minus R2. Okay. Now, what does that? So, okay, that's just what I get from the assumption. But what do I know about this remainder R1 minus R2?
Has to be 0.
Yeah, it has to be 0 because M divides AB. But by the uniqueness part of the division algorithm, R1 minus R2 equals 0 since M actually divides A minus B, right? That's why the uniqueness is useful. There can only be one remainder and we know it's 0. So we're done. Okay. So A congruent to B mod M. So having the same remainder mod M is equivalent to M dividing the difference. That's what this proposition is saying. And it's a very useful proposition. Let's call this proposition 1. Any questions about this?
Yeah, could you repeat again? Why do we want to show that R1 is equal to R2?
Well, what's the definition of A congruent to B modulo M? It's that A mod M equals B mod M, right? But what's A mod M? It's the remainder when you divide A by M. So that's R1. Does that make sense?
No,
Like let's go back to a mod d. A mod d here is the definition is it's the remainder when you divide a by d, right?
right.
And here, what's the definition of a congruent to b mod m? It's the remainders are the same.
Oh,
A
okay.
mod m equals b mod m. And so maybe the line you're missing is, here in this proof, R1 equals a mod m and R2 equals b mod m. Maybe that's what you're missing, right?
Gotcha. Thank you.
So after we got like a minus b equals to m times q1 minus q2 plus r1 minus r2, it's like you said, you wrote that, but by the uniqueness of the division of, so if they're unique, they should like, so it means that they are the same, or there's like other process.
Yeah, okay. No, you're okay. So there's actually one more step which I missed. So a is equal to this, and let's assume without loss of generality that R1 is greater than or equal to R2. So you're right. We need to add one more line here, which I missed, which I skipped. So assume without loss of generality that R1 is greater than or equal to R2. So again, this difference R1 minus R2 is non-negative and strictly less than D. So that's important because going back to the division algorithm, the statement was there are unique Q and R satisfying this equation, A equals DQ plus R, and R is between 0 and D, right? And so what I've done here is I said, hey, look, I found some numbers that satisfy the equation and that property that R1 minus R2 is non-negative and strictly less than D. So then by the uniqueness, it has to be equal to 0 because I know the remainder was 0. Does that make sense?
Yeah.
Okay, so I'm going to take a little break since it looks like, well, no harm taking a break. Actually, I took a class the other day that took an hour 40 and I realized the break is really good. So let's take a half-minute break.
May I see the screen? Like,
yes, so I'm going to use the break also to refresh my screen. It'll be back in a moment. It
okay.
serves two purposes.